Okay, let's get started. First of all, hello and thank you all for joining us today. On behalf of Flexcompute and Friendship Systems, I would like to welcome you to today's webinar on the cloud-based aerodynamic optimization of a compressor stator using an efficient workflow based on the tools Flow360 and CAESES. And yeah, let's get started. Let me introduce myself. My name is Mattia. I'm responsible for sales and marketing here at Friendship Systems. I've been with the company for about 15 years, and I've previously worked in the pre-sales and engineering teams here. I'm originally a naval architect, but I've spent much of the last years working on turbomachinery and working with our turbomachinery customers and on the development of turbomachinery functionality. So I'm joined today on the Flexcompute side by Payam. He is an aerospace engineer at Flexcompute. He has a Master of Science from the TU Kaiserslautern. So Flexcompute is a US company, but Payam is actually located close to us here in Germany. And his interests are in aerodynamic shape optimization, design and automation, which is very fitting to the topic of today's webinar, of course. Before we actually get started with the content of the webinar, I have a few housekeeping issues that I would like to mention. Today's webinar will be recorded and it will be made available to you for replay. So one day after the webinar has completed, you will get an email with a link to the recording that you can, of course, watch or share with your colleagues. If you have any questions throughout the webinar, feel free to interact with us. You can submit your questions in the GoToWebinar panel, and we'll try to address as many questions as possible at the end of the webinar in a short Q&A session. If we don't get to your question, then we will try to follow up with you, so don't worry. All right, let's get started with the actual content. And before I want to talk about our case study that we're presenting here today, I would like to give you a very brief introduction about our tool CAESES that we used in this case study. And what is CAESES? So CAESES, first and foremost, is a highly specialized CAD system for the design of turbomachinery. It has a focus on the efficient modeling of the most complex geometries that we encounter in this field of application. It's fully customizable for tailor-made workflows, so you can customize everything in the process, the geometry parameterization, the workflow so that it suits kind of your needs. And we have a focus on a reliable variant generation for design studies. So it's not a pure CAD system, but the end goal of what we're doing is we want to run optimization studies, design explorations, optimizations, and we need a very reliable means of generating geometry variants. But CAESES is not only a CAD system, but it's also an automation environment where you can integrate arbitrary simulation tools and involve them in the optimization process. And it is also a comprehensive optimization platform where you can run these kind of design exploration and optimization studies. So this is kind of the summary of what I've just mentioned, the main component of CAESES. We have the CAD environment on the one side, the optimization environment on the other side, and then what is called automation in the middle is basically the interface where you can connect CAESES to arbitrary external simulation tools. Most of the times we're dealing with CFD solvers, but it can also be structural solvers or any other type of calculations. So as I mentioned, that the Probably most important and most unique component of CAESES is the specialized CAD environment. So a typical question that comes up is, why would I need another CAD system? So everyone is working with some sort of CAD system nowadays. And in our experience, the people we talk to and our customers, they kind of the bottlenecks that they're mostly dealing with when they want to set up and run automated design processes are related to the handling of the geometry. So for example, geometry variation with these, I will call them traditional CAD systems, it's often difficult. So it means when you start changing parameter values with an optimizer, for example, you run into problems of regenerating the geometry. The geometry model is broken, or you get infeasible geometries. Another important point are constraints. So we want to optimize the geometry for performance, for the best possible performance, but of course we want to get a result that fulfills all the constraints that we have, maybe related to manufacturing or also to packaging, things like that. And we want to make sure that we involve these constraints in the optimization process, which is also a, let's say, task that is often difficult with traditional CAD systems. And then there's a few other additional points like simulation ready CAD geometry. So the quality of the CAD model that comes out of many CAD systems is not necessarily ready to be used directly for simulation and might need some manual interaction, which is not helpful for automation. Or as we're dealing with quite complex, often free-formed geometries, we quite often run into the problems that too many parameters scale up the effort for optimization, making it very inefficient. Or maybe on the other hand, the problem that we want to control very specific geometrical properties that are critical for performance, and we don't have that control in the way that we want to. And these are basically a bunch of reasons that we are addressing with our tool in CAESES. So CAESES is not a general purpose CAD system, but it's really a highly specialized CAD system with a focus on geometry variation for geometry optimization, basically. All right, let's take a very quick glimpse into specifically turbomachinery design capabilities in CAESES. So CAESES is used also for other applications like marine, automotive, industrial machinery, and so on. But one of our main fields of application is turbomachinery, and we have a set of dedicated capabilities for these kind of applications. So the turbomachinery applications that we deal with are, for example, turbochargers. So as you can see here, including all the aerodynamic components involved there, gas and steam turbines, so mostly axial machinery, but also things like propellers, but fans and blowers, pumps, or hydro turbines. So basically the complete gamut of turbomachinery applications can be covered. And in order to cover these applications, we provide a comprehensive modeling environment within CAESES to model bladed geometries, but also casing geometries. You can also do things like end wall contouring for non-axisymmetric hubs, but also include additional flow structures that are maybe in the secondary flow path or not the kind of main bladed components, such as we see here, portage shroud on a compressor or cooling structures in the blade, or bypasses, wastegates for turbochargers and things like that. You can also analyze imported geometries. So if you have an existing model or you have a database of blade designs and so on, then you can import these geometries, extract parametric values from these geometries. And also if you have a parametric model, a new parametric model of the similar geometry, you can perform some fitting to match these imported geometries. In addition, as an alternative approach, we have also some morphing capabilities in CAESES that you can use to do some quick adjustments of imported geometries. And we also have the possibility to implement as a user customized preliminary design steps. So we don't have a preliminary design system on board in CAESES. We are more located on the CAD end, but you can also implement your kind of custom preliminary design workflows within CAESES. There is a extensive scripting and coding environment within CAESES. If we look specifically at blade modeling, you can do parametric modeling for all types of blades, radial, axial, mixed flow. There is specific airfoil and transformation methods for axial machines, other methods for radial machines. As I said, everything is really customizable, so it's not based on black box models where you can just change some parameters, but you can really fine-tune everything to your liking, create your own parameterizations. There is also tuning possibilities for every shape detail that you find on the geometry, like fillets, scalloping, leading edge shapes, blade tips, as well as the possibility to consider manufacturing constraints like machining constraints if you want to have flank milling or casted geometries and so on. And finally, interfacing, of course, is important. So you have the possibility to fully integrate CAESES into existing workflows. So it's scriptable, it runs in batch mode, so you can include it also in third-party workflows. You can also couple it to external preliminary design tools and import the output from these preliminary design and extract parameters and so on. You can create in an automated way kind of the necessary pre-processing steps for mesh generation, so you can export fluid domains, solid domains. You can export kind of proprietary export formats like GeoMTurbo or TurboGrid for Cadence or ANSYS mesh generation tools. And there is, in addition, possibilities to couple to adjoin CFD results in order to get sensitivity results for the geometry parameters from adjoin CFD. And we also have a tight integration into ANSYS Workbench through these CAESES Workbench apps. All right, so much to give you an introduction about the tool, so you have an idea of what we're using here and what the capabilities are. And now I would like to move forward and talk about our specific application case, the Compressor Stator optimization that we performed together with Flexcompute. The test case that we're using here is the so-called TU Berlin TurboLab Stator. You will find more information online if you search for TU Berlin TurboLab Stator. It's a stator that is located or can be located in a measurement rig at the TU Berlin, and it was created specifically to have a representative stator geometry similar to what is used in modern jet engine compressors. This was the kind of idea. I think it was created originally for kind of a competition where different involved parties performed optimization and submitted their results, and then there was a symposium where these results were compared. And as the task of this stator is to turn the incoming swirling flow into an axial flow. So we have in front of the stator, we might have some rotor stages, and we have a flow that is incoming to the stator that has a certain swirl, and we want to turn it into as pure axial flow as possible with a minimal pressure loss across the stator. So these are our objectives for the optimization that we performed. We want to minimize the total pressure loss across the stator. We also want to minimize the deviation from the pure axial flow at the exit of the stator. And we had a lot of, or maybe also in the context of this test case that was set up, the geometry was supposed to be created by additive manufacturing, the blade geometries to be tested afterwards. So there is a lot of freedom in the shape because due to the additive manufacturing there is little restrictions on the shapes we can realize, but there is a few constraints on the geometry that are due to assembly reasons. Like you can see in the picture on the side, we have some bolting holes in the blade, so the blade needs to have a certain thickness so we can fit these holes and things like that to make sure that the final blade can also be assembled for this test rig. All right, so let's start now into the workflow that we did on this test optimization test case. So the first step is geometry parameterization. So the goal that we want to achieve is that we want to have a variable geometry model. So basically a model of the geometry that by changing parameters we can change, and then we can automatically generate different variables, different variants of these geometry. And one approach to do this is to create a fully parametric model of the geometry in CAESES, which is what we have done here. And as I mentioned before, the other possibility is that we can apply morphing to an existing CAD model, and regardless of which way we're choosing here, the result is always that we have the possibility to create geometry variants. And the parametric geometry can also be based on an existing CAD model, which was actually the case here. So we can also take basically an existing CAD model, extract some data from that, and use that as a basis to create a new parametric definition. So how did we go about this in CAESES for this specific test case? We modeled the stator with our dedicated turbomachinery workflow in CAESES. So as I said, turbomachinery is one of the major applications of CAESES, and we have some dedicated workflows here. And basically here for a turbomachine, it consists of creating, so to say, stepwise certain objects that are linked to each other. So basically, if you look at this tree structure at the right hand side, you see that we start with the kind of parent object, which is the turbo machine, and then to this turbo machine we can add components. And what we did here, we added a bladed component, which is our stator, and then we can define this bladed components by specifying our meridional contours, so hub and shroud contour basically, and then based on that we can then start building the blade. And this is kind of the central element in our model and in most of turbo machines, is the blade shape, and in this case we used a so-called airfoil blade surface, which basically means is we're creating a blade that is based on an airfoil definition. So the first component here is a 2D parametric airfoil definition that we select here in our airfoil blade. We can select a 2D airfoil definition from a library of existing definitions that we provide with CAESES with different airfoil definitions. But as I mentioned, you can also customize everything and create a custom airfoil definition to your liking. The second part is that we then need a transformation to transform the 2D airfoil into a 3D airfoil for the final blade. There is different transformations we can choose here, from a simple cylindrical coordinates transformation, which might work well for a fan blade or something simpler, or if you have a kind of non-straight, non-cylindrical hub and shroud contours, then you can use a more advanced ZR theta transformation, where you can provide hub and shroud contour, stacking axis, and then the airfoils will be transformed into stream surfaces that are located between hub and shroud. And then there's a few other transformations that are applied to the airfoil, like rotating the airfoil by the stagger angle, or scaling it up with a chord value, so you can model the 2D airfoil in a normalized way and then scale it up with a chord, or you can model it directly with the real chord in 2D, and then the scaling is just one. And then finally, once we have selected our parametric airfoil definition up here, we will also see all the parameters that are part of this 2D definition that we can then use to manipulate the shape of the airfoil, like we see here. So these are the parameters that appeared for this definition that we used here. And for each one of these parameters, you can provide either a constant value, so it means you will use a constant value throughout the blade, throughout the span of the blade from hub to shroud, or alternatively you can provide a distribution function, a radial distribution function that describes how this parameter changes from hub to shroud. Okay, so let's look at these steps, the actual steps for these geometries. As I said, we start with our meridional contours, so hub and shroud contour, and our stacking axis. This is the leading edge shape in this case. And then in the second step, we create our blade surface in the way that I just described, with this airfoil blade surface, which is based on our 2D definition, which you can see here with the parameters indicated there. And then we have some radial distribution functions that describe how these parameters that we see highlighted here change from hub to shroud. So at the beginning, we have a very simple blade, just straight shape, and our values are basically constant. But as you can see, we have some control points on these distribution functions that we can manipulate with parameters, and then we can change these values throughout the span of the blade. We then can create the hub surface, which in this case, actually we included some end wall contouring in the modeling or in the setup of this model. But maybe as a disclaimer, we didn't use the end wall contouring in the optimization process because we had already a very large number of variables, and so we left that part out. We might follow up with some additional optimizations here. After we have created the hub surface, we can basically create a solid for our sector. So we have basically closed our blade at the tip. We have created the kind of slice here of the hub. And at this point, you can see we have also included a fillet between the hub and the blade. And then we can multiply this slice to create our full 360 degrees stator wheel. And then we can also create our shroud end wall surface. And basically, this is the kind of finalized model. So for the optimization purposes, we had defined 55 design parameters for the geometry, and I'm going to go through them, not all 55, but in groups, so you can get an idea of what kind of variation we performed on the geometry. So first of all, we have 7 parameters that control the shape of the stacking axis. So basically we can move the control points of the stacking axis in theta. This is the circumferential angle direction. And if this is the animation here for the shroud point, which basically moves the stacking axis as a line. But if we control the intermediate points, as you can see here, we can also deviate from this just linear shape and introduce some curvature at certain positions here along the span, which you can see here as an example. Then we have 5 parameters that control the so-called metal angle. So this is the angle here at the leading edge of the blade, and you can see here the variation again of the shroudmost control point. You can see the in 3D and in 2D, and just as an example here, you can also see the variation of the metal angle for one of the intermediate points, which you see has then an effect in the midspan of the blade. Okay, let's go through the next groups of parameters. So we have again 5 design parameters for the camber of the airfoil, again to control the 5 control points of this radial distribution. Then we have 5 parameters to control the stagger angle of the airfoil, 4 control points to control the radius of the leading edge. Yeah, you can see here, I think mostly in this 2D plot. Then we have another parameter which is a bit hard to see, which controls the so-called ellipse factor, which allows you basically to change the shape of the leading edge from circular to elliptical. We have the control on 5 span-wise positions of the maximum thickness of the blade. And we can control on 4 span-wise position the maximum thickness position in chordwise direction. And then we have 2 parameters here, thickness factor 1, which controls basically the sharpness of the blade in the forward part in front of the maximum thickness, and the thickness factor 2, which controls the sharpness aft of the maximum thickness position, both controlled in 4 span-wise positions. And another parameter for the spread angle at the trailing edge, again in 4 span-wise positions. And another factor which I think is almost impossible to see in the animations, which also controls the shape of the trailing edge. So these are all kind of the overview of all of our design parameters, and then of course we can combine the variation of all these design parameters together, and then as you can see here in this animation, we can get a quite wide range of variation and a wide range of blade shapes that result from these parameters. All right, so this was the kind of first step in our workflow, where we created a variable geometry model. And now the next step is to couple CAESES to our flow solver, the external simulation code, which is in this case is Flow360, so that we can supply all the geometry variants for simulation and get the simulation results for each of these variants back into CAESES. And what we're using for that is our so-called software connector, which is a generic interface for coupling CAESES to arbitrary external analysis tools. And basically in this interface here, we define the data exchange between CAESES and the external tool. So the input and output files. We can parameterize values in input files so that we can also combine geometry variation with the variation of different other operational parameters, for example. And the upper part of the interface provides all the output from CAESES to the external tool. So the geometry export, in this case we exported the flow domain of a single blade passage, and then we have additional input files that are needed to control the external tool. Payam will say more about this in a minute. And then in the lower part of the interface, we define the result files that CAESES will load when the computation is finished and use, for example, to extract certain values that we use as objectives or constraints in the optimization process. So this is basically very simply how the interfacing to the external tool is done. And once we have connected the simulation to the geometry variation, then we can go to the optimization step and perform an optimization on the geometry. And this is where I would like to hand over, so to say, to Payam, who will say a little bit more about the tool Flow360 that we use here and how that is controlled, and then what was done in the optimization process and what kind of results we got. So Payam, I'm gonna switch over to you as a presenter, and yeah, the floor is yours. Thank you.
Thank you very much, Mattia, for the introduction and the great presentation. So hello, everyone. And the second part of this webinar, we are going to show how Flow360 is going to be used for aerodynamic shape optimization of these data. So this is a little introduction about Flexcompute. Flexcompute is founded in 2015. Co-founders are from MIT and Stanford. We are developing advanced computing technology in order to accelerate innovation. We are leveraging emerging computing technology in order to break the limits of traditional computation for industrial simulations. We are able to do steady-state simulation in minutes, transient simulation in hours, and flight database in days. We are actively working on our technology in order to maintain our 360-second standards and improve it. We have a fully compressible Navier-Stokes solver. It's a node center edge-based finite volume method code. We support mixed element unstructured meshes. We can perform a steady state and transient using SA or K-omega assisted turbulence models. We do hybrid trans LES. We have AFD models. We have cross-media automated meshing and rotating domains, and even more are coming. Our unprecedented speed is coming from the combination of the hardware and software architects. Flexcompute offers two products, Flow360, our CFD code, and Tidy3D, our electromagnetic solver. Here is Flow360 in numbers. In particular, for this case, for example, we ran 383 simulations. The average solver time for this almost 400 simulations is about 10 minutes, and the average mesh size is about 52 million points. So let's have a demo of Flow360 and see how easily we can launch a simulation. Here, after you enter our web user interface, you can switch to the volume mesh panel. There, you can upload your volume mesh, or you can start generating your mesh from the surface mesh panel. After you upload your volume mesh, you see it in the list. You can click on the your mesh, and then you can see different part of your mesh. For example, here we have blade fillet, or we can go and see the, for example, suction side of the vein. And you can find the mesh quality metrics in this part, including area ratio, aspect ratio, first layer thickness, and have your judgment how good your mesh is suited for your CFD simulation. In the visualization tab, you can see your case, or you can see your mesh. You can zoom in, zoom out. You can move it left and right. You can click on the wireframe in order to see the mesh. After you are satisfied with your mesh, you can easily click on the new case. You can go forward and fill the blanks here, or you can use upload JSON file and upload a case configuration. This JSON or case configuration includes all the necessary and required information in order to launch a simulation. You can give it a name like demo, and then you can click on submit. After you click on submit, you might be getting validation warning that we communicate to our users. For example, this is a very coarse mesh. And for that reason, it was saying that most probably the Y plus on this mesh is going to exceed the desirable value. And then you can switch to the cases panel. You can see your case is already uploaded. After a few minutes, it's going to change to pre-processing, and then it's going to start running. So let's follow up on the slide size. So as I explained, you can see the mesh quality metrics in the volume meshes with respect to different surface area of your mesh, and have your judgment about the quality of your mesh. In the cases panel, you will find case information, and also you will find your solver setting, how you can set the parameters with respect to the Navier solver, with respect to the turbulence solver, and etc. Then in the cases panel again, when you switch to the convergence tab, you can see, you can track how well your simulation is converging while it's running on our server. Here, for example, continuity and the turbulence are shown. Also at the bottom of the same page, you will find the convergence of your forces with respect to different parts of your surface solution. Then you can switch to the visualization tab, and in the visualization tab, you will find your solution after your case is completed. You can turn them on and off. You can see the CPU distribution, and you can have your engineering analysis on our web user interface. So here for this cases study, we have a parametric model coming from the cases. Cases takes initial design variables, pass it to the parametric model. The parametric model generates the geometry model. We take the geometry, pass it to our preprocessor. Our preprocessor generates the mesh, pass it to the CFD solver, Flow360, and the Flow360 runs it on our server, completes, and after that, we pass it to the post-processor, and post-processor extract the seems that I got the chat. Okay, nothing. And sorry about the interruption. I thought you're not hearing me. Okay, the post-processor extract the value of the objective function. Here, our objective function is in augmented form. It's a total pressure coefficient at the exit panel and the flow angle deviation at the exit panel. The value of the objective function goes to the optimizer, and then optimizer goes either to the next level or it is complete. The whole process is being completed. In case of continuation, so new sets of design variables are being generated and is being passed to the parametric model, and the parametric model updates the geometry model and then pass it to the preprocessor. And this is how one design loop is being completed. So here you can find the definition of the augmented objective value. And we started with 64 design variables, and then later we performed the optimization with 55. Okay. So here, let's have a validation study before performing the optimization. On the top, you will find the flow conditions, including the total pressure at the inlet, total temperature at the inlet, and the flow suit angle and the pitch angle. So at the bottom, the Mach contour is shown. This Mach contour is the inlet condition applied to the inlet number. And in order to obtain this non-uniform distribution over the inlet, we use the total pressure variation with radius, inlet pitch variation with radius, and sewer angle variation with radius from the test rig measurement. And Then we performed the mesh refinement study. For the mesh refinement study, we generated 5 different mesh levels. This table shows different parameters with respect to those meshes. It's a mixed element mesh family. The coarsest mesh is about 2 million and the finest mesh is about 100 million points. These are the solution for the baseline geometry on different mesh levels. And as you see that these two objectives, exit flow angle at the bottom and the pressure loss coefficient at the bottom, are pointing to a number. And also at the same time, we are obtaining the target mass flow rate, which is 9.3. And based on the comparison of the solution, the baseline, and the experimental results published, we come to the conclusion that we can perform the optimization with confidence on level 2. Here is a comparison between the flow solution on the suction side, a stream lines on the suction side of the baseline geometry in comparison to the experiment shown on the top left, and the Hydra CFD, which is Rolls-Royce CFD solver on the top right. And when you compare the experiment with the Flow360 solution on the bottom, you can see that we captured this flow separation very well. For the experiment and the CFD results of Hydra, you can refer to the reference. And also here, we compare the total pressure loss coefficient at the measurement plane and compare that against experiment and Hydra CFD at the design point. And for the level 2, we have a good agreement as it shows here. And then we started the optimization. For the optimization, we used a multi-objective MOGA genetic algorithm with respect to objective functions. And for that, we use 55 design variables. In order to start optimization, first we use a Sobol algorithm in order to create 350 samples. These samples are ran in 3 parts, 100 parts first, 150 parts then, and then 100 parts second, and then 150 parts at the end, in order to make sure that the workflow works fine and there is no problem there. And after that, we obtain the solution with respect to our sampling domain. We performed optimization. We ran 3 design iterations with 5 solutions first, which is shown through green triangles on this plot, and then we performed the second round of the optimization, which is shown by a square pink in the plot. And at the end, we performed a check design iteration to make sure that the results we got, the optimum results we got from the second round is okay. Here is how the whole process looks like. So this animation here shows how the sampling is performed, and we obtain the value of the objective functions. The pink dot in the plot. The pink dot in the plot shows the baseline, and those blue dots are the samples. After 350 samples are done, we start doing the optimization. So for these 2 objective functions, we would like to reduce both of them. So we want to get closer and closer to the left bottom corner of these objective values. So here, the first round of the optimization started. Here is the second round of the optimization. And at the end, we have the design check iteration. As you see that we can see a Pareto front here. And after this, we have, with respect to this baseline shown with the yellow dot, circle dot, we have a Pareto front optimum solutions. And these are the Pareto front optimum solutions that we are interested in. So this table shows the Pareto front optimum solutions were compared against the baseline. And also we have the optimum geometry from the Rolls-Royce optimization, and then we ran that in order to compare the results, our results against that optimum solution. So design 15 from the second round of the optimization and design 12 at the second round of the optimization are desirable. We achieved a maximum reduction in the total pressure loss coefficient at design 15, and we obtained a maximum reduction in the exit flow deviation at the exit plane at design 12. And when we are comparing the optimum solution, for example, design 15, we see that we could almost 3% reduce the total pressure loss coefficient at outlet, about 3% more than the Rolls-Royce optimum solution. Here is a comparison of the streamlines. On the suction side of the lane, on the top is an experiment for the baseline solution. On the bottom left is a baseline solution from the Flow360. In the mid, you see the streamline on the optimum solution from the Flow360. And on the bottom right corner, you see a streamline on the optimum geometry from Rolls-Royce, and they are very comparable. So here at the end, there is a qualitative comparison between the baseline solution shown on the left, the optimum solution from the Rolls-Royce shown in the middle, and the optimum solution from the Flow360 shown at the right. And at the bottom, in the bottom table, you will find the value of the objective functions. Thank you very much for the time and for the attention. Thank you, Mattia. So I can switch to you, and if you have questions, please let me know.
Excellent. Thank you very much, Payam. I'll just switch to my screen here for the backdrop of the Q&A. Yeah, as I said, we have a little bit of time now where we can discuss some questions that might have come up. So as I said, feel free, if you still have questions, to post some questions here. We'll try to answer as many as we can. I have maybe, before we get started with the actual questions, I have just two clarifications that I wanted to add, maybe for Payam's presentation. First of all, about the optimization, just in case you're wondering, that the optimization runs that we performed after the initial design space explorations, we had a very low number of designs. So the reason here is that these were so-called surrogate-assisted optimizations. So we used the database that we created in the initial design exploration with the Sobol algorithm, as Payam mentioned, and then we fed that database into a surrogate model. And the optimization, so the multi-objective genetic optimization that was performed there, was performed on the surrogate model, and then we only do additional CFD computations in a very limited amount, and those are the ones that are shown. So say when we get an optimum, it's computed, and then we feed that CFD data into the database as well, refine it, and so on. So this is maybe the explanation of what has happened there in these optimization rounds. And one further comment, maybe in case you're wondering, at the end there was some comparison to the so-called Rolls-Royce geometry. The reason for this is, as I said, this TurboLab stator was created for this kind of symposium and competition where different people submitted their optimization work and optimization results, and the best result there, so to say the winner, if you want, of the competition was a design submitted by Rolls-Royce. So I think Rolls-Royce performed this optimization together with the Queen's University in Belfast, and that's, so to say, what we're comparing to there. That's the reason. All right. Let's start to look into some questions. First question can you share this presentation or any paper about this study? Yes, we can. So there is some presentations about the original study, as I mentioned, some publications that I think were mentioned by Payam in his presentation, and we will share this video recording of the webinar afterwards, so you can watch it again. And I'm pretty sure we will also create some publications, probably at least a blog post about this case study. So there will be some more material that you can look into in the future. I have a question here about the CFD runs. So the question here is, what number of CPUs or GPUs were used for each CFD run? Payam, can you say something?
Yes. So the computation is performed on our side. So as I said, that our unprecedented speed comes from the combination of the hardware and software. There is no specific number of the CPU or GPU dedicated to specific cases. Everything is flexible. That's why we are having a Flexcompute. But we have a very, very nice speed, as you see. For example, for these 383 cases, the average simulation runtime on the solver side was about 8 minutes, as about 10 minutes.
All right, thank you. Another question here is, how are the workflows automated? So I can just briefly say something about the cases side, which I think you've seen more or less already. I mean, we have a parameterized geometry model, and we have our optimization environment in cases which provides algorithms, and these algorithms basically get a list of design parameters that they can change with bounds, and then they will change the values. This will update the geometry. We will create a new geometry, and that geometry is then exported by cases through the interface that I showed to the external simulation tool. And then we get the results back, read the results, evaluate them, for example, see if the objective has improved or gotten worse, and then we can proceed with additional variants. And maybe, Payam, there is a little bit that you can say about the automation on the on your side. So basically,
yeah. So automation is based. So if the question is how the mesh is being generated, mesh is automated through solid meshing. We automatically generate the mesh over a solid, and the solid is watertight. So we get a watertight BREP from cases, and then we generate that. And in order to customize the mesh, we use surface naming, and based on the surface naming, we can tune the surface mesh over a particular region, for example, leading edge to leading edge. And then after the mesh is completed, the mesh is being uploaded. Flow360 has a very rich Python API, and through Python API, everything can be automated. You can validate, you can post-process, and you can pre-process. And at the end, what is connected to cases is a Python script with my Flow360 conditionals as a user. And so every user can use this Python API and automate the whole process.
All right. Yeah, thank you. And I can confirm that it worked, I think, very easily. You saw in the interface set up in cases that basically we export the geometry, we export the Python script and the JSON file with the case set up, and then everything runs externally and we get the results back. So it's really simple. I'm not 100% sure I understand this question. It's about what input parameters did you use or the MOGA model gave for the final optimized model's CFD? So I'm not sure I understand this correctly, but basically the optimization algorithm, as I said, selects different sets of parameter values for the geometry, and which set is then the best one is basically decided by the algorithm. So I mean, we have a multi-objective optimization here, so we have, of course, a Pareto frontier, not a single optimum design, but yeah, we get a set of geometry variables, and that design is computed, and then we got the results that Payam showed. And yeah, maybe in a similar direction, there is a question regarding how the best geometry differs from the baseline. So I don't know if you could see it, but there were some pictures in Payam's presentation that showed the difference. So basically, the main difference that you can state is the baseline geometry, as you can see in the backdrop here, actually was a straight blade, very simple straight blade shape with constant parameter values throughout the span. And as a result of the optimization, we got a kind of more wavy geometry, wavy shape that, so to say, where individual span-wise positions and span-wise airfoils try to, so to say, get the shape where they influence the flow field behind in a favorable way. Here's a question about kind of other applicability for CAESES and Flow360. So for CAESES, I mean, both tools are not specific to turbomachinery. As I mentioned already, we have dedicated functionality in CAESES for turbomachinery, but we can also cover a lot of other applications. One of our major other applications is marine. So we do a lot of yeah, CAESES is used a lot, let's say, for ship hull optimizations, but also things like propellers, rudders, and so on, everything that is related to the hydrodynamics of a ship. But also things like powertrain is strong, where you want to optimize internal geometries of combustion engines, for example, intake ports, things like that, or also electric powertrain, mostly related to cooling of electronics and batteries, and valves are a popular application. Yeah, medical devices, things like that. So it's really a general purpose tool for shape optimization of especially complex geometries. Yeah, maybe how about Flow360? What are other good applications for your tool, and what popular applications?
Yeah, so Flow360 can be used for all sorts of CFD application as long as we have that feature. For example, we have porous media, we have we have lots of applications on external aerodynamics, design and evaluation, and with rotating boundaries. But also at Flexcompute, we are developing our tools for emerging technology. So if you have a particular application that needs a particular need from a CFD solver, we can help you a lot on that side.
All right, I would say that's all the time we have for today. We need to come to an end. So I would like to thank everyone for joining this webinar. I'm very sorry for the glitch with the audio. I've done many webinars in the past, and this is the first time this has happened. I don't know, still don't know the reason, but yeah, I hope it was still okay. And yeah, of course, feel free to reach out to us if you want to discuss your applications or learn more about our tools. You can connect, of course, the folks at Flexcompute, Payam, for example. and look at some general information about their solver on their website. And same obviously for CAESES. If you want to learn more about the tool, you can reach out to us at our contact email address. But you can also, if you want to try the tool firsthand, you can download CAESES from our website. You can register for a trial license, and there's a bunch of tutorials that come with the tool, as well as a video tutorial page where you can find a lot of learning material, and then make your own experiences with the tool. And if you need some support, then of course you can get in contact with us. Watch out for more webinars coming up in the future, as well as additional material. As I said, we'll try to publish a bit more about this case study that we've done. And until then, thank you again for joining the webinar, and have a good rest of the day. Bye-bye, and hope to see you soon.
Thank you, Mattia, for the webinar, and thank you everyone for attending. Have a nice day.
Thank you, Payam.